Okay. Due to a time conflict on Monday morning, I'm pre-recording uh, this lecture for lesson 3.5. So I'll just jump directly into it. Okay. Um, Now, previously, you've been using the derivative to find local uh, minima and maxima of functions. So in that case, you're taking derivative setting equals 0 and classifying the critical point that you find as either a maximum, minimum, or neither, and also finding out where a function is increasing or decreasing. Here, what we're doing is, and when you find a local maximum, minimum, a function could still be have a larger or smaller value. Like if you find a local maximum, that doesn't rule out the function being greater elsewhere. It's just local near that point. Here, we're focusing on a given function on a certain domain, and we want to find the absolute maximum minimum. So where does the function reach its largest value, larger than any other on this interval? So we're going to be doing a lot of the same things. We are still going to be looking for critical points because they will help us to find the absolute maximum or minimum. Okay, so to illustrate the process, we have 7 problems in total, and I'll certainly do the word problems. Okay, well, actually, I believe I really do have. Yes, okay, there are 8 problems altogether. I thought so. And I'll certainly be doing the word problems and the selection of these other ones because these first 5, they really are pretty much all the same. But I will include, when I post the notes, full solutions to all 8 of these problems. Okay. So just to illustrate the procedure, I'm actually going to start with problem number 2. Okay, so we have this function, 2x cubed minus 54x, on this interval. And we want to find the x values within this interval at which this function assumes its smallest and largest values. So those are the absolute minimum and the absolute maximum. Okay. So together, those are referred to as the absolute extrema. And I want to point out that Hawks expects the answer to be entered as an ordered pair. So you'll specify the x where the minimum occurs and the y value. So you have to substitute that into the original function, and then similar for the absolute maximum. So 2 ordered pairs are what you will enter for your final answer in Hawks. So how do we go about finding the absolute maximum minimum of a given function on a given interval? So those are the 2 pieces of information you'll always be given: function and interval. First thing you do, like in previous lessons, for finding a max or min of any kind, you will take the derivative. So here's our function. So we'll just go ahead and apply the power rule there to get, so the 3 comes down and we get 6x squared. And then here we apply the coefficient rule, and derivative of minus 54x is just minus 54. So here's our derivative. Then what we do is set a derivative equal to 0 to find critical points or critical values. So for that, we'll set f prime equal to 0. So that means that 6x squared minus 54 is set to 0. So then we'll rearrange and isolate x squared. And then we take the square root and we get, in this case, plus or minus 3. So these are the 2 critical points that we have. Now, when you get critical points for problems like these, you must check, do they fall within this interval? Because if not, they're excluded. So you're trying to find points on this interval at which a function might reach a maximum or minimum, but only looking at this interval. So in this case, plus or minus 3 both fall within this interval from -9 to 5, so we will consider both of them. Now, those are not the only points at which the max or min might occur. You have to consider the endpoints. Now, the endpoints generally will not be critical points, but what could happen is, for example, what if as we approach x equals 5, the function might keep increasing, and so when it hits the endpoint 5, because it's increasing, and it actually is in this case, that value that it hits at x equals 5 might be larger than any of the other values that f assumes within the interval, including at critical points. So for problems like these, where you're trying to find the absolute max and min, you basically have candidates to consider where the max and min might be. What are these candidates? They are the critical points that are within this interval, and you must consider the two endpoints. So in this case, we have 4 points altogether at which the absolute max or min might occur. The critical points -3 and 3, and the endpoints -9 and 5. So once we have our candidates for the absolute max or min, how do we determine which is which? Substitute all the candidates into the original function. So let's just see what values we get. Because we're only going to have generally a few points to check, go ahead and check them all. Largest value will be the absolute max, smallest value will be the absolute min. So if we go ahead and do that, we'll just go through the different candidates. Oops. Okay, so just going from left to right, we consider x equal to -9. So just go ahead and substitute x equal -9 into a function, and we're going to get a very negative number in this case. So -9 cubed is -729 if we multiply that by 2, and then we have 54 -54 times -9 is going to give us a positive number, but still going to get a very negative number here. That's looking like a good candidate for the absolute minimum, but we won't know for sure until we check all the points. And so next we move on to x equal -3 and substitute it into the original function. And we get this value plus 108. Okay. So far, that is the absolute max, but we'll find out when we plug in the other 2 points. Now I move on to +3. And we get -108. So that falls in between these two. So this point will be neither the absolute max nor the absolute min. And then finally, one more point, x equals 5. That's the right endpoint of the interval. And what we get is -20. So as x goes from 3 to 5, it's way down here at -108. It is increasing all the way up to -20. But this value at x equals -3 is still larger. So now that we've obtained the values of f of x at all 4 candidates, so -9, -3, 3, and 5, we just look at the 4 values and see which is the largest, which is the smallest. So this is definitely the largest. It's the only one that's even positive. And then this value is the smallest. In other words, it's just the most negative. So -972. So now we can conclude that we have that the absolute maximum is at x equals -3, and then the y value is 108. And then the absolute minimum is at x equals -9, and the y value is -972. So that's a procedure for any one of these absolute max and min problems. Take a derivative, set it equal to 0, get any critical points, consider only critical points that fall in this interval. Also consider the endpoints. So those are your candidates for the absolute max and min. whatever candidates you have, whether they be endpoints or critical points, substitute all of them into the original function f of x. Largest value is the absolute max, smallest value is the absolute min. Okay, let's see. Look at this function, this problem next, number 4. Okay. So we proceed like before. We take a derivative of 6x minus 8, and we just, for coefficient rule, all we get is 6. Well, that's never going to be 0, so there are no critical points. So the endpoints are the only values that we have to consider. So that's something that can happen. It's possible the derivative will not be 0 at all on this interval. In fact, this derivative is not 0 anywhere in the real number line. So we substitute in only minus 3 and 3. So for minus 3, we get minus 26. And then we substitute x equal plus 3. And we get 10. So then x equals 3 must be the absolute maximum. And then x equals minus 3 must be the absolute minimum. Now, if we look at the kind of function that we have here, the graph of this function is just a line. And it's a line with a positive slope. So a function like that, its derivative is positive, it's always increasing. So that tells you right there that the left endpoint is going to be where the minimum, the right endpoint is where the maximum is going to be because of a positive slope. If it's had a negative slope, it'd be the other way around. You still have to substitute these values into the function to get the actual y values to enter your answer. But when it's a line like this, then you can tell from that what's going to happen. A function that's a line not going to have any critical points. Or at least when a line is a positive or negative slope as opposed to a 0 slope. Okay. Here we have a function of a very different sort, where we have a negative power of x. So let's see what happens there. And we're considering the interval from 12 to 18. Now this function is undefined at x equals 0, but that's not going to be a problem for us because that's outside of the interval that we're considering. So we go ahead and take the derivative, and a good idea is to rewrite the function. So I'm going to write it as minus 1536 x to the minus 1. That's more conducive to taking the power, taking a derivative using a power rule. So then we get minus 6. Should write it this way. From a coefficient rule, and then the exponent comes down to minus 1. So then we have a plus 1536 x to the minus 2, which we can then rewrite as x squared in the denominator because it's a negative power of x. So that is our derivative. So like before, set it equals 0 to find any critical points. So I'm setting this equal to 0 and rearranging. Then I multiply both sides by x squared. And then I'm going to divide both sides by 6. I want to get x squared by itself. So we move a 6 down here. The x squared is moved up here. And we get x squared is equal to 256. Now we take a square root. Now, generally we consider that we have a positive and negative square roots, plus or minus 16. However, keep in mind, we're looking at the absolute maximum on this interval from 12 to 18. Which of these critical points actually fall within this interval? Well, minus 16 doesn't. So that is not included as a candidate. So we consider the other critical point, x equals positive 16, and then the two endpoints, 12 and 18. So it's only these 3 points that we will substitute into the original function to get the max and min. So starting with x equals 12. So we go back to the original function and substitute those, and we get minus 200. And then we just keep going from left to right. So x equals 16 is next. And we get a value that's a little less negative, so minus 192. So this can no longer be the absolute. Well, it could still be the absolute min. It can't be the absolute max. This value is greater. But then let's see what happens at x equal to 18, so the other endpoint. And we get this very positive value, 193.3 repeating. So here is where the absolute maximum occurs, and then the absolute minimum is at the other endpoint at x equals 12. Okay. Oh, wait. Sorry. That was labeled wrong. It's x equals 18. Okay, so that's positive. So this value, that was the largest of the three, goes here, and the x value, which was assumed 18, is goes in for the x value. Okay. What I'll do now are the three word problems. Now, notice in all three of these problems, a range of values is given for x. So here, x is between 0 and 23. So this is a closed interval that you will consider. I say closed because the endpoints are meant to be included in the interval. So two ways of specifying a closed interval using inequalities like this, where it must be less than or equal to, or greater than or equal to, instead of strictly less than or strictly greater than. Or using interval notation. So here we use square brackets, and that indicates that the endpoints 12 and 18 are part of the interval. Whereas if I'd use parentheses, which you actually did use a couple lessons back for specifying intervals of increasing and decreasing, that means the endpoints are not included. Okay. So here we're finding the absolute maximum of this revenue function on this interval. So we will consider the endpoints, 0 and 23, and any critical points that happen to occur in between from looking at the derivative. All right, so here, like before, we take a derivative of our original function, so using a coefficient and then the power rule, and then we find where it is equal to 0. Okay, so we'll set the revenue function's derivative equals 0. Okay, so we set it's equal to 0, and then rearrange, divide by minus 12, and we get x equals 16. Always check, does the critical point fall within the interval of consideration? In this case, it does. So now we have three candidates for the absolute max and min, but endpoint, left endpoint 0, critical point 16, right endpoint 23. So all of them must be, all right, so I'll write that down. Equals 0, 16, 23. For either max or min. So we go ahead and substitute in x equals 0. And we get 0 in that case, which makes sense. If you don't produce any units, you won't get any revenue. And then x equals 16, the critical point. And we get 1536 for revenue in that case. And finally, x equals 23. And we get 1242. So that's a little bit less So here we have the absolute minimum at 0, and then we have the absolute maximum at 1536. Now, if we look back at the problem, unlike our previous problems where we asked for both the absolute max and min, here we only care about the max. So here this is the largest value on the entire interval, so that is where the maximum revenue occurs. All right, so at x equals 16 units is where that happened. Actually, clean this up. Then I'm going to put this on a new page. All right, so we plugged in everything. This is largest value at x equals 16. That's where the maximum revenue occurred. Okay. Here we have revenue function that's given for selling X units of salt, and then a cost function for producing that. So putting the two together, we would obtain a profit function, and it's profit that we want to maximize on this interval. So we're considering X between 0 and 25 units. What number of units in this range will give a maximum profit? All right, so the first thing to do is actually get the profit function. So that's going to be revenue minus cost. So we'll go ahead and fill in what those functions are. And then we have some like terms to combine, like these two like terms, and then these two also. And we wind up, and watch your signs, be sure to put both functions in parentheses when you substitute them in, because this minus has to be distributed through all of this. So a lot of students make sign mistakes on those. So once we have the profit function, then like before, you take a derivative using a power rule, and this is what we get. So then we need to look for critical points by setting a derivative equal to 0 as usual. And we get 4. And 4 does fall within the interval under consideration from 0 to 25. So that is a candidate for the absolute maximum profit. So now we have our free candidates 0, 4, and 25 to substitute into the profit function. Now, it would seem kind of odd to substitute 0 units in for a profit function, but for other applications, it's definitely necessary to consider all candidates. But we'll just go through motions. So, of course, no units, then negative profit of -5 because there's some fixed cost there. And then you substitute in the critical point, x equal 4. See what profit we get in that case, so 75. So far, this is the largest value. And then we substitute in the right endpoint, x equal 25. And, well, actually, hold on. Okay. This 525 squared is 625. Okay, yeah. Okay. So yes, we get a very negative profit in that case. So here we have a maximum. So at 4 units, profit is maximized. Okay. Do one more. All right, so here's a cost function. Here we want to minimize cost. We're looking for the absolute minimum on this interval, x going from 1 to 244. But it's not just cost, I apologize, average cost. So as I've just shown here, it's important to pay attention to every word of a problem description. So we're finding the minimum of average cost. Okay. So first we need the average cost function, and that is defined by taking the cost function and dividing by x. So go ahead and do that, and we break it up into 3 fractions and then simplify as much as possible. So this is what we get for the average cost. Now you take the derivative. The derivative of 1 over x is minus 1 over x squared, because 1 over x is the same as x to the minus 1. You apply the power rule to that, and you get minus x to the minus 2. So here, I've rewritten the function for taking a derivative, so you can more easily see how you get the derivative from a power rule. You don't have to do that. If you keep in mind the derivative of 1 over x is minus 1 over x squared, you can just jump directly to this. And then taking the rest of the derivative, 1.7 is a constant, and then 43x gives us 43 by the coefficient rule. So we go ahead and set that equal to 0. And see what we get. What happened? Okay. All right, so that is set equal to 0. And then we just do some rearranging. So if we multiply both sides by x squared, and then divide both sides by, or in this case, I just negated both sides. But if I multiply both sides by x, and then divide both sides by 43, then we get that. Now that's something that you want to work out on your calculator, and what you get is 3,136 equals x squared. And if you take the square root of that, what you get is plus or minus 56. Now, if we look at the critical points and compare that to the interval under consideration, x going from 1 to 244, well, minus 56 is not in the interval, so we ignore it. But x equals 56 plus 56, that is worthy of consideration. So now we have our candidates. The absolute minimum, x equal 1, the left endpoint, and then 56, the critical point, and then 244, the right endpoint. Right. So first, x equals 1. And we find that the average cost in that case is pretty high. So now we substitute in the critical point, 56, and we get a much lower average cost in that case. And finally, we substitute in the right endpoint, x equal 244. And we get a higher cost in that case. So the lowest cost happened right here. So this minus 56 was already excluded. So x equals plus 56. That is where the absolute minimum occurs. Okay. So To summarize, if you're asked to find the absolute minimum or absolute maximum of a given function on a given closed interval, so x between 2 points including endpoints, then take the derivative, set it equal to 0 to get critical points. Only consider critical points that are within the interval under consideration, and you take your endpoints and valid critical points and substitute all of them into the original function, as is shown here. Largest value gives you the absolute max, smallest value gives you the absolute minimum. So that's the procedure throughout this lesson. So be sure to distinguish, as like when you get to the second test, some problems will ask you for local max or min, a function without specifying an interval. Other problems will ask for the absolute extrema or absolute max or absolute min of a function on a particular interval that you must consider. So be sure to distinguish which procedure, distinguish these types of problems so that you follow a proper procedure for each one. And that's why it's important to pay attention to the way in which the problem is worded. Some will ask for absolute extrema, or you're trying to find a value of x that maximizes or minimizes some function on some range of x values. So that's when you're going to follow the procedure shown today. All right, so that concludes this lesson. There's a few problems that I did not touch, but I will include the solutions to those problems as well when I post these notes.